Today we're going to talk about power. All right, we're going to talk about the physics definition and equation of power. Okay, and power is a rate. Power tells us the rate at which work is done. Okay, so when you hear the word rate, what does that make you think of? Yeah, change of. Typically, rate is going to tell you how fast, right? Velocity is a rate. Acceleration is a rate. Power is now a rate. Okay, so it's telling us how quickly something is getting done, right? And so power tells us the rate at which work is done. The unit for power is going to be a watt. Capital W, watt. Right, where do we see watts at?
Light bulbs.
Electricity, good. Light bulbs, yep, that's where we see watts. Okay, and a watt is just indicated by a capital W. Okay, and what a watt stands for means it tells us 1 joule of work is being done every second. Okay, so it's joules per second. We can also measure power in horsepower. Where do we hear the term horsepower at? Yeah, good, in vehicles. Okay, and so there's a conversion to get us from horsepower to watts. And that conversion is 746 watts equals 1 horsepower. Okay, so horsepower is a pretty big unit. It takes 746 watts to make 1 horsepower. So here's our equation for power. All right, here's our equation. Does anyone know what that bar over the P means? Not repeating. Just means average. Okay, so you don't have to include that bar over there. I won't ever write it again. Your book does. That's why I put it on there. You don't need to include that. But what we're talking about here is power is going to be work over time. Work over time. Okay, and we talked about work being force times displacement, but we also talked about work being a change in energy. Okay, some sort of energy transformation. So when we say that power is the energy transformed over time, that means we have a couple different ways we could solve for work, which means there's a couple different ways we could solve for power. Okay? So just kind of keep that in the back of your mind. There's lots of ways we can solve for work. What are the 2 main ways that we know right now how to solve for work? Force times distance or displacement, good. And what's the other kind? What's the other way we know? Yeah, good. Delta KE, so change in kinetic energy. And that's the energy transformation part that we were talking about. But work is any type of change in energy. So we're going to hit our other type of energy today, potential energy. So work could also be a change in potential energy as well. Okay, we need to remember that power and energy are not the same thing. They don't represent the same thing. They don't mean the same thing. Just because they're measured in the same unit, don't get confused because they're not the same, right? When we talk about work and when we talk about energy, we can start thinking about it in terms of ourselves. And what do we have the power to do? Okay? The ability that we have to do work as humans is limited. Okay? And what is it that limits your individual ability to do some form of work? Right? To apply a distance over a certain force. What is it that limits a human's ability to do infinite amounts of work? Fatigue is one, good. What else? Can you think of anything? Can you sprint nonstop for 2 hours? No? Right? I can't sprint nonstop for 20 seconds. Right? Why is that? Don't be careful how you answer that. Okay? Why is that in most humans, why can't they sprint for an extended period of time? The amount of power that we output is not only affected by the energy or the work that we put in, but it's also affected by the time it takes us to do it. Okay? So if I wanted to go up 2 flights of stairs, I could sprint up those 2 flights of stairs, and it wouldn't take very much time. Right? If I sprint and I expend a lot of energy, it doesn't take a lot of time. But it takes more energy. All right? If I was going to walk up 2 flights of stairs, okay, I'm covering the same amount of distance, okay, so therefore I'm technically doing the same amount of work, but I'm using much more time, which means less power output. Okay, are we seeing the relationship between those two? The work that I do to get up to the top of the stairs is physics-wise the same, okay, because I'm covering the same amount of distance, but the time it takes me to do it is going to affect the amount of power that I output. Okay, that's going to be what our lab is centered around today. Okay, we could do more work, or if we climb higher, if you walk at a slower rate. So if we're talking about the same amount of power output, we would have to adjust the time that it takes us to do that. And this is the last thing that we talked about. Our chemical conversions within our body can only happen so fast. Okay, so that's another limiting factor to the amount of energy or the amount of power that we can put out. Sorry, you don't have to have all those little bullets. We're just going to talk about them a little bit, okay? You don't have to have them all down there for them. All right. Let's see here. Before we look at the problem, I want to walk you through this set of equations here, okay? We say that power, which is capital P, is equal to work over time, okay? So these are just kind of a sequence of equations going from one to the next. So what is another equation that we can use for work? Force times displacement. So all I did here was substitute power equals force times displacement over time. That's it. Okay? The last thing that I'm going to look at is, if you look at displacement over time, what variable does that give us? Distance over time or displacement over time? It gives us velocity. So we can substitute for displacement over time, velocity. Okay, so this is another equation that we can use to solve for power. Okay, so I would make sure that this one and this one for sure are on your equation sheet. You can have that middle guy too, just as kind of a reminder or another helpful version if you've got those variables. That's up to you. Okay, so this gives us a pretty simple way to solve for power. The force that we apply times the speed at which we're applying that force. Okay, so let's look at this problem here. Student uses 140 newtons to push a block up a ramp at constant velocity 2.2 meters per second. What is their power output? Okay, here we're not as concerned with displacement and time because we took velocity into account, which already takes those two things for us. So this is really as easy as it seems. 140 newtons times 2.2 meters per second. Okay, and what would our units be here for power? Watts, good. I think you can go ahead and do this one on your own. Electric motor lifts an elevator 9 meters in 15 seconds by exerting a force of 12,000 newtons. Let's find the power output of that motor. Good. Okay. Here our force and our displacement were already parallel to each other. Okay, that's important. They were both going vertically. We have to make sure that we're paying attention. If that force is applied at an angle, we have to find that component that's parallel to the force. This one was already parallel, so it's easy for us. Okay? Let's go ahead and see how many horsepower this motor is putting out. Okay, so if I want to go from from watts to horsepower, what should I do? Good, divide by 746. So if I put it in a T-chart, it would look like this. 746 watts is 1 horsepower. Horsepower, you just can abbreviate HP. Okay. We should always think about getting a smaller number of horsepower than we do of watts. Okay, so if you get a horsepower that's larger than your number of watts, you're in trouble. Okay, make sure that we have a smaller number. So is that what we got for horsepower, hopefully? Okay, HP. Very good. Okay, we do need to make sure that we know how to do that conversion. So we're going to talk about potential energy. What was the type of energy we talked about last class? Kinetic. Good. And what does that kinetic mean? Motion. Good. So what does an object have to have for it to have kinetic energy? It's got to have movement. It's got to have a velocity. Okay? So now we're going to talk about potential energy. So potential energy in and of itself means that the object has the potential to do something. Okay? It has the potential to do work on something. It has the potential to have work done on it. Okay? But potential energy depends on where an object is located. Okay? Kinetic energy does not. It just has to be in motion. But potential energy really makes a difference in terms of how far is it off the ground? How far can it fall? Just little things like that. It does depend on where that object is located. Okay? Okay, the first main type of potential energy that we're going to talk about, we're going to do two. The first main type is called gravitational potential energy. This is the simplest form of potential energy that we have. Okay, so gravitational potential energy means that something has the potential for gravity to act on it. Okay, and to act on it in such a way that it would make it move, kind of. Okay, so you don't have to write this part down, just think through it. Okay, when a brick is held in the air, it has potential energy relative to its position on the earth. So if I'm holding something in the air, okay, a brick, I'm holding this in the air, it has the potential, if I let go of it, to do what? To fall, yeah, to drop, okay? That means it has the potential for gravity to act on it. Okay, if something's sitting on a table, doesn't it still have the potential to fall? Yes. The only time it doesn't have the potential to fall would be if it was where?
On the floor.
On the ground. On the ground. Or on its lowest possible position, right? Okay, so let's think about if we're on a roller coaster, okay, and we think about if that thing stays on the track. Okay, we're thinking best case scenario here. If it hits that valley part of its path, that would lead to no potential energy at the bottom, okay, because potentially it's not going to go off the track, we hope. Okay, we're thinking perfect world here, okay? But just think about that kind of situation. Something that makes it specific that it has potential energy is that if it falls and it hits something on the ground, okay, so let's visualize this. There's a nail that's just started in a piece of wood on the ground, okay? Just started means the nail is sitting there, it's ready to be hammered in, okay? This thing falls on it, hits the head of the nail. What would happen to the nail? Would it move? Would it drive further into it? Okay, think about this being heavier. Okay, we're not using markers. Okay, think about something else. Okay, if it hits that nail on the head, it should displace that nail a little bit, right? We're applying a force. It would cause that nail to move. It would displace the nail, which means work has been done. Okay, so when something has the potential to do work on another object, it has potential energy. Okay, when something is hanging above the ground, it has potential energy. Okay. All right, so the equation for gravitational potential energy is mgh. Okay, you don't have to put the little g there. You can if you want, but it just means gravity. M times g times h. Okay, which means M probably stands for what? Mass, which has to be in kilograms, good. G is standing for gravity, good. Okay, which is 9.8. And H is probably what? Yeah, it's height off the ground. Okay, so that means an object that's right here, does it have more or less potential energy than an object that's way up here? It has less, right? The higher you get, the more potential. Okay, just think about that. The higher you drop something, the more impact it's going to have when it hits, which means the more work that it can do. Okay, that's what we just talked about. Work done by gravity of the mass as it moves from point 1 to point 2 is equal to the difference in potential energy. So work, again, is equal to the change in potential energy. And I don't really even need you to include this negative. It's saying that the gravitational work is going to be negative. We talked about work being a scalar, so it doesn't have to include that direction, okay? But again, your book does. But what I want you to make sure that you have in your notes is this equation. Work equals change in potential energy, okay? And this is just an expansion of that. M times G times the change in height, right? Mass isn't going to change. Mass is not going to change. Gravity is not going to change. But the height of our object as it falls and as work is being done would change, okay? So as we look at the change in potential energy as an object falls through the air, there is work being done, and what's the force that's doing that work? Or what's the system that's doing that work? Gravity. Okay, so that's why we're saying that the work done by gravity is equal to the change in potential energy. Okay, this would have to be gravitational potential energy in order for that to work. Okay, does that kind of make sense? Kind of? Okay. So let's look at our roller coaster example. Physics textbooks and problems love to use roller coasters in this chapter. Okay, so we will see lots of roller coaster problems. Okay, that's because it gives us a good visualization as to when something's at its highest point and when it's at its lowest point. Okay, so we're talking here, we are at the top of our roller coaster. Okay, and when we look at the roller coaster, we can kind of reset this here at the ground level, right? Because that's the lowest that, realistically it's going to go. It's not going to fall to the ground, hopefully, okay? We're talking about ideal conditions here for a roller coaster. So at the top, before it starts, it has to have all potential energy, right? Because is it in motion? No. And it's at its highest point before it starts. We have no energy, right? Or no velocity. That means no kinetic energy. As it falls down to its lowest point, okay, does it have the potential to drop any further? No. But is it in motion? Does it have a velocity at that point? Yes, so it's all kinetic energy. As it starts climbing back to its highest point, somewhere in between, is it still in motion? Yes. Does it have the potential to drop back down? Yes, so it has both. Okay? So potential and kinetic energy is kind of like a sliding scale, right? We either have one or the other or both. Okay? What would be the only situation in which you have neither of those things? Yeah. Sitting on the ground, not moving. Okay, that would be the only situation in which we'd have neither of those things. Okay? Does that kind of make sense? Okay, so think of potential and kinetic energy as kind of a sliding scale, right? We got to have one or the other or both. Okay? All right, so let's try one here. If you want to draw out this basic roller coaster, you can, but we're going to get started on this one here in just a couple minutes. Okay, so we don't know anything about what's happening at point A, so we're going to just kind of reset that at the ground level. Okay, that's going to be our starting point. We don't really know, is it in motion here, is it not? We have no idea what's happening. So all we're going to do is we're going to look at the difference basically between point A and point B. Okay, and see what gravitational potential does it, what happens to the change. Do we expect it to gain potential energy as it goes to point B or to lose potential energy as it goes to point B? Gain. Good, right? We're going upward, we're getting higher and higher and higher, which means we're gaining potential energy. So we want to find out what the potential energy is at point B. Okay, so I would take M times G times H. Okay, I don't care about what the height is at point A. This height could be 25 meters. This height could be 35 meters. I don't care. I'm just looking at the difference between those, which we know is 10. Okay, does that part make sense? So you have the ability in this chapter to kind of reset yourself depending on the 2 points that you're looking at. Okay, so potential energy here would be mass times gravity times the height. Okay, what do we think that potential energy would probably be measured in? Just joules. Yep, energy is joules. Okay, so just joules. Just look at our roller coaster again. Let's say we started right here. Let's say that this was our starting point. At point C, okay, wait. At point B, what would we have? All potential, all kinetic, or both? All potential. At point C, what would we have? Both. Good. At point D, what would we have? Kinetic. Good. E, what would we have? Both. What about F? Both. This is why. We've got all this energy stored up from, let's say, 20 meters worth of height. Okay? And we drop down and we come back up maybe only 8 meters worth of height. Okay? We still have a lot of energy stored up to go all the way back up to the top. Okay? So if we're not at our maximum height again, that means we're going to have both types of energy at point F. Okay? So you got to reach your maximum height. Right? If we think about an object, let's just say like a skateboard, you know, I don't know what those things are. Yeah, half pipe. Okay, if you start at the top, isn't he usually able to make it all the way back up to the other side on the first try, right? As he goes back to the other side, is he usually able to make it to the top? Okay, realistically, maybe. Theoretically, yes, they should be able to. Okay, in a half pipe, this skateboarder should be able to go back and forth, top to top, the whole time. Okay, in a perfect physics world, that should happen. What would cause that to not happen? Friction, right? Friction takes out some energy from this guy as he's going up and down this pipe. Okay, but realistically, he should be able to go to that maximum height every single time. Will he ever go past it? He should never be able to go past it, right? He's only got this much amount of energy, so he should never be able to go past it. Okay, does that kind of make sense? So on that roller coaster example, you can think of it kind of like as a half pipe. If he kept going, he would be able to go all the way back up to his highest point again. Okay? All right. All right, so now we're going to apply this gravitational potential energy to power. So as you go up something, as you're overcoming gravity, you are putting out power. You have to do power. You have to output power to overcome gravity. You're overcoming that gravitational force as you run up. Oops. Okay? So this is another way that we can solve for power. Okay, power is equal to work over time. And we know that work is also equal to change in potential energy. Okay, so let's think about this guy at the bottom of the stairs. As he's right here, does he have any potential energy? No, he has 0 potential energy. As he gets to the top, does he have potential energy? Yes, so he does have it at the top. Okay, so that means as we look at change in potential energy, we would say power is equal to mgh minus 0 over time. Okay, why did I put this minus 0 right here? Yeah, it doesn't have any at the beginning, right? Delta means final minus initial over the time it takes him. Okay, so that means I would say 70 times 9.8 times the total height of the stairs, which is 4.5 meters. Do I care how many steps he took? Do I care how many steps there are in that flight of stairs? No, I care about the total height that he traveled, okay, to overcome gravity there. .03 horsepower. Okay, 771.75 watts and 1.03 horsepower. Okay. Cliff's 122-meter vertical climb. The record time, 4 minutes 25, was achieved by 65 kilogram man. What was his average power output? Average power output doesn't mean anything different to us. We're still just going to solve for power. Okay. Do we care if he zigzagged up this hill? Do we care if he climbed it straight up 100%? It makes no difference to us. Okay. So the path that we take to get there doesn't matter. Okay, so we say m times gravity times the height over 265 seconds. Is that right? Okay. And so what do we get for our power output here? 293.26 watts. Okay. So was this guy, did this guy have a greater power output or lesser power output than the one that sprinted up the stairs? Much less, right? Even though he climbed a much farther distance, but it took him a much longer time. So it's all about the rate at which that was done. Do we think the guy that sprinted up the stairs, could he have sustained that power output for 122 meters? No, right? That's what we were talking about, the limitations that we have on our body. We can't do it, okay? That's what we're talking about, limitations, okay? All right, last little section that we're going to cover today has to do with the power output of cars and their vehicles, okay? So when humans output power going up something, we output power in order to overcome gravity. Okay, so when cars output power, they do it to overcome friction, to get started, right? To get put into motion. They're trying to overcome friction. Okay, and the cars are not limited by their, bodies. Okay, realistically, kind of they are. Okay, but they're limited by their motor. Okay, and every motor has its own individual horsepower rating. Power when you are accelerating, speeding up, and when you're climbing a hill. Okay, why would we need more power when we're climbing a hill? Yeah, friction and gravity. Good. We have to overcome friction and gravity. There's two things working against us when we go up a hill. Okay. Oops, sorry. So here's our equation that we can use for cars. Okay, work. We know that work is also equal to change in kinetic energy. Okay, so does this equation look familiar? 1/2 mv squared. That is our equation for kinetic energy. So this equation that's given in this box right here is realistically telling us what about our starting velocity. Do we see this? Okay, since I only have one term here for kinetic energy, what does that tell us our starting must be? 0, right? We left off this minus 0 here. Okay, we could have an equation that looks like this. Power equals 1/2 mv squared minus 1/2 mv squared over time. Okay, that would be our true definition of work. Okay, but we're assuming here that we're starting from rest, which means our initial kinetic energy would be 0. Okay, if we wanted to find out how much work it took to go from 10 meters per second to 20 meters per second, okay, or how much power was outputted during that time, we would need to include both of those terms of kinetic energy. Okay, does that make sense? Yes or no? Okay, so you need to put some version of this equation, either one, on your equation sheet. Okay, either or both. Okay, so a car accelerates from rest to 15 meters per second in 4 seconds. Calculate the power output of the car. We're going to ignore the force of friction. We just know that it's putting this much power to overcome that. Okay, and why did I include this minus 0 here? Starting at rest. Good. Initially, we have no kinetic energy because it's starting at rest. You can leave that minus 0 off. I just want to show you the whole picture. Let's go ahead and calculate it in watts and in horsepower. Is that what we had for watts? 28,125. Okay, and to put it in horsepower, we should go from where? Go where? Divide by. Very powerful car. Or very powerful use of the car right there. Not so much.